if you have any interest in power plants or gas turbine engines or automotive turbochargers, then this video is for you. This video is all about what's called turbine efficiency. Now, this is the real world, so I can assure you that this is covered in an academic thermodynamics class, but it's about as real world as you can get because practicing engineers use the definition of turbine efficiency throughout all of engineering. And so this is an important idea to grasp. It's also going to be an important idea to grasp and understand because I can nearly totally guarantee that a problem regarding turbine efficiency is going to appear at least several times in quizzes and tests and your final exam so that you'll be able to perform well in class. It will be good that you grasp this definition of what's called turbine efficiency. So what's a turbine in the first place? So you remember that back in Chapter 4, I've got a video for you that you could go back to chapter key points, look at the playlist, and click on Chapter 4, Part 7 to refresh your memory on what is a turbine in the first place. And of course, here I've shown on the right, this is a cutaway view of a steam turbine. And here on the left is a cutaway of an air turbine that uses a starter for gas turbine engines. So go back and refresh your memory about what is a turbine in the first place if it's not pretty clear in your mind. So how about some basics? So it is important to get you up to speed on a reminder about the difference between W dot out, that's output power, and little w for an open system. And so, of course, you remember a turbine clearly is an open system. And typically in this class, we deal with steady state, steady flow open systems. Things are operating steadily. And of course, for a turbine, you basically got one inlet and one outlet. And so on my basic sketch, I've got M dot, which is the same at states 1 and 2, inlet state 1, outlet state 2. I'm showing on my sketch that W dot of the turbine is out. Now, I haven't shown Q dot in for a reason, but on my sketch, but there's a reason for that, and I'll talk about that here in a minute. But it is important to remember the relationship between little w out for an open system is defined as W dot out, output power, divided by M dot mass flow rate for steady state, steady flow. So that helps you get up to speed with the material covered in your book because your textbook author uses little w for an open system all the time. Let's see, units of little w, kilojoules per kilogram, or BTUs per pound. That's an important thing to grasp and remember. Let's look at sort of the basics of a reversible adiabatic steam turbine. I hope you've got some experience with this from your homework problem solving instead of me explaining the gory details right now. But let's see, here's our hand-drawn sketch of what might be given in a homework or an engineering problem. And you'll see that the inlet pressure and temperature is typically given. So that's typically going to be a superheated vapor, typically going into a steam turbine. The sketch is shown here. Interesting here how typically we don't show a Q dot in. And that's because for most of our real world practical applications, nearly all of them, our turbine is considered to be fully insulated. So I haven't even shown Q dot in equals 0 on my sketch, but I am showing W dot out on my sketch. And I'm showing what's coming out here. Only the pressure is given, 40 kPa. So this could be a typical homework problem. And so the assignment could be determine W dot over M dot, since neither are given, find little w of the turbine. And so problem also could be, I'm also need to tell you that this turbine is reversible and adiabatic. Let's see, adiabatic, fully insulated, reversible. That means there's no unrestrained expansion in this turbine. What would the TS diagram look like for the steam turbine process? Well, we're going to start out at superheated vapor. You would discover that 4 megapascals and 400 degrees C is a superheated vapor phase. And if the process 1 to 2 is reversible and adiabatic, you can draw a vertical line. That's constant entropy. And I can draw it as a solid line. That's the indication to yourself and to other engineers that this is a quasi-equilibrium or a reversible process. Now, what's the area under the curve here for this? That's 0. Remember, the area under the curve on a TS diagram is heat transfer. And so you visually see that there's no heat transfer for this isentropic process. Okay, so there you go. There's the setup. You should be kind of familiar with this setup before we get into some definitions here. Okay. Now let's say that I said, oh, well, wait a minute. The turbine is still insulated, but there's some things going on with the turbine blades that make it irreversible. So there's some unrestrained expansion going on in this particular turbine design. And so we're not getting, we don't have an isentropic turbine. We have some irreversibilities going on in there, some unrestrained expansion. Now, it's still adiabatic. We're still fully insulated. I'm just saying we're irreversible. Okay, so what would our process look like on the TS diagram for an irreversible adiabatic turbine? So I've shown, here's a dash line, and I think you can do some head scratching and go back to your fundamentals about entropy production rate for a process to see that if a turbine is fully insulated and it's irreversible, what's S2 going to be? Or numerically, is it going to be greater than, equal to, or less than S1, little s? How will little s2 compare to little s1? Oh, well, it has to be greater than. So little s for an insulated irreversible turbine is going to be greater than S2. So let's see how I've changed my sketch. I'm going to call this process that reversible adiabatic process 1 to 2I. For me, in my world, that's 2 isentropic. In your textbook, here's the little yellow note here. In your textbook, the textbook calls it 2S. Just be aware of that. I'm not going to change my practice just because the book does something else. Now let's look at this actual process. I call my state 2, little s. I call it 2A for 2 actual. I got tremendous results. This is how my professors taught me to do it. And it helped me really understand the difference between the actual outlet state and the isentropic outlet state by calling it 2A for actual and 2I for 2 isentropic. I have shown it as a dashed line, and that's important. You show an irreversible adiabatic turbine as a dashed line because it's irreversible. You can't visualize the area under the curve for the heat transfer. That's why you show it as a dashed line. Now your textbook calls this actual state just 2. And that's fine. That's fine. That's not the way I do it. And so in my work, I call it 2A, and I find it much easier to keep straight when I call the actual outlet state 2A and the isentropic reversible adiabatic state 2I. All right. So we're making some progress. We're getting some familiarity with a TS diagram for a steam turbine right now. Now for a little bit of a mental test. We just looked at 2 processes for a steam turbine. Process 1 to 2I, reversible and adiabatic, also known as isentropic. And then we looked at a similar process, but it's irreversible, process 1 to 2A. So you saw that the 1 state was the same, but the 2 state were 2 different states on the TS diagram. That's important to recognize, okay? This isn't just formula stuff. This is important for visualize on TS diagram. Process 1 to 2A is irreversible and adiabatic. Let's see, in common, both adiabatic, One's reversible, one's irreversible. So use some common sense 101. When you have that, for those two processes, which do you figure which steam turbine would produce more power? 1 to 2i or 1 to 2a? Which do you figure? What does your common sense tell you? Which would you get more power out of that steam turbine to run a generator? 1 to 2i or 1 to 2a? What do you figure? Common sense says 1 to 2i. A reversible adiabatic turbine, using common sense, for the same inlet state and the same outlet pressure, is going to give you more output power than the irreversible and adiabatic turbine. So that's a true statement. That check is true. That's consistent with common sense 101. Now, next question. Let's apply common sense 101 is if we define turbine efficiency, if we could define turbine efficiency, would you expect that efficiency to be a number equal to 1, greater than 1, or less than 1? Which do you figure an efficiency value would be? Less than 1, greater than 1, or exactly equal to 1? Common sense says an efficiency value is going to be a number less than 100%, less than 1.0. That is correct. That is common sense 101. And efficiency had better be less than 100%. So now we can define isentropic turbine efficiency right out of the textbook, but we can do it using some common sense. And here it is. So now we define isentropic turbine efficiency. Here it is. This is not N. By the way, this is Greek letter eta. Eta turbine. That's not N turbine. Okay. Don't get out of Virginia Tech and call this N turbine. You will embarrass yourself and Virginia Tech if you call this N turbine. All right. It's eta, Greek letter eta. Eta turbine. Turbine efficiency is defined as little w actual divided by little w isentropic. So in other words, it's the work from process 1 to 2a divided by the work, W dot over M dot, from 1 to 2i. That is the definition of isentropic turbine efficiency. It is less than or equal to 100%, is never, never, never more than 100%. I would claim that you can figure this out in your head without writing this down on your formula sheet. Common sense should enable you to write this definition of turbine efficiency down on your own. Now, it is common practice to be given a turbine efficiency or to have to figure out what it is, okay? But it's more common for me as a practicing engineer, is to find the isentropic turbine efficiency to be given, to find the isentropic work, W isentropic, using basic computations, to be given turbine efficiency, and then have to back calculate W dot over M dot actual. That is the most common approach for turbine computations in engineering practice rather than determine the turbine efficiency. All right, so here we go. Some more notes. The devil is in the details here. And so I've created a video in the past where I give 3 worked out example problems for making these types of turbine efficiency calculations. So if you go to my example problems open systems playlist and click on turbine calcs, you're going to be able to get 3 example problems worked out. But I don't want to just stop there. I want to give you some other notes in this video on how to prepare yourself to do turbine efficiency calculations, because you can count on being given this in this chapter and also in future chapters for steam power plants and for gas turbine engine calculations. So very important. So here's a recap. We have reviewed the objective of turbine. It looks like I'm not providing you with some tips. So gosh, let's go back a slide. Yikes. I got confused between my turbine efficiency video and my pump efficiency video. So I'm going to have to chase you back to, if you want to see example problems for turbine calculations, both air turbines and steam turbines, go to my example problems, open systems playlist, and click on turbine calcs. Oops. All right, so we have reached the recap. We've reviewed the objective of a turbine, and that's produce power. The objective of a turbine is to produce rotating power, whether it be a steam turbine or the turbine section of a gas turbine engine or the turbine section of a automotive turbocharger. We have defined isentropic turbine efficiency, and my claim is, rather than writing it down as a formula, you can figure out the turbine efficiency using Common Sense 101. Efficiency's got to be a number less than 100%. I think I remember that I would get less work from an actual turbine than I would from an isentropic reversible adiabatic turbine. So therefore, turbine efficiency must be little w actual divided by little w isentropic. And the devil's in the details. And let me see if I can chase you to another video where I work out the details of turbine calculations. So, oops, I caught myself. I thought I was going to give you some words of wisdom how to step through a turbine calculation. I see that I'm now reminded in my mind that I did not do it because the computational steps you use for analyzing a steam turbine are dramatically different than the computational steps you use for analyzing an air turbine or a turbine that's using an ideal gas as the working fluid. So that'll have to be an oops on my part. So I do hope you go and look at that separate turbine calculations video for some tips on detailed calculations.